Namaste and welcome back to JEE Physics with Typical Monk. This is class 13, Simple Harmonic Motion and Oscillations. Pull a mass on a spring and let it go. It does not simply return to rest. It overshoots the center, comes back, overshoots again, and repeats forever in an ideal world. That is simple harmonic motion, and it is born from one single rule. A restoring force, always pulling back towards the center, in exact proportion to how far the mass has strayed. Today, we make that end the stance calculable. Its equation, its energy, and its time period. One idea at a time. Here is what you will learn today. First, the sham condition. Acceleration equals minus omega squared times x, and its solution, x equals a sine of omega t plus phi. Second, velocity acceleration and the phase between them. Third, the energy in shma, the half k squared that shuttles between kinetic and potential. Fourth, the spring mass system, in series and in parallel, and the simple pendulum. And fifth, damped and forced oscillations, resonance, and a set of G drills. One idea at a time. 4 ideas. Run this entire chapter. Look at them together first. The sham condition. The acceleration is proportional to minus the displacement. Acceleration equals minus omega squared x. The force always pulls back towards the center. The solution, x equals the sine of omega t plus phi, a pure sine in time of amplitude a. The time period, t equals 2 pi over omega. For a spring, 2 pi root m over k. For a pendulum, 2 pi root m over g, and notice no amplitude appears. And the energy, the total energy is half k squared, and it stays constant. It simply shuttles back and forth between the kinetic and the potential. Now look at the picture. Displacement, velocity, and acceleration, each drawn against time, stacked one above the other. Displacement, x equal a sine omega t, a pure sine starting from the mean position and rising. Velocity, v equals a omega cosine omega t. It leads the displacement by 90 degrees, reaching its peak exactly as x passes through the center, fastest at the middle. Acceleration, equals minus a omega squared sine omega t. It is exactly opposite to the displacement, and it is largest at the extremes where the restoring pole is strongest. And all three share one period, 2 pi over omega. Only their phases differ. Each curve is a quarter cycle apart from the next. Now, the kinematics in detail. The velocity, b equals omega root a squared minus x squared. It is maximum, a omega, at the mean position, and it falls to 0 at the extremes. The acceleration, a equals minus omega squared x. It is 0 at the mean, maximum, omega squared a, at the extremes, and always directed back towards the center. And the velocity displacement graph is an ellipse squared the velocity relation, and it becomes v squared over omega squared plus x squared over a squared equals 1, a tidy ellipse. And the phase, the velocity leads the displacement by 90 degrees, and the acceleration leads the velocity by a further 90, which puts it exactly opposite to the displacement. Let us work a numerical. A 1 kilogram mass sits on a spring of stiffness 100 newtons per meter. Find the period, then join two such springs, first in parallel, then in series. The single spring, T equals 2 pi root m over k, 2 pi root 1 over 100, which is 2 pi over 10, about 0.63 seconds. In parallel. Springs in parallel add directly. The effective stiffness is 100 plus 100, 200 newtons per meter. Stiffer. Its period, t equals 2 pi root 1 over 200, about 0.44 seconds. Stiffer means a shorter period. In series, the reciprocals add 1 over the effective k is 1 over 100 plus 1 over 100. So the effective k is 50 softer, and the period is about 0.89 seconds. So the answer? The single spring, 0.63 seconds. Parallel is stiffer and shorter. Series is softer and longer. Springs add their k in parallel and add reciprocals in series. Now the energy and how it moves. Look at the plot of energy against displacement. The potential energy P equals half kx squared, a parabola, 0 at the center and maximum at the extremes where the spring is most stretched. The kinetic energy Ka equals half k times squared minus x squared, the mirror parabola, maximum at the center where the mass moves fastest and 0 at the extremes. And the total is constant. Kinetic plus potential equals half Ka squared. At every single point, the energy simply shuttles between the two, never lost. And the total can also be written half m omega squared a squared. Exactly the same energy, since omega squared equals k over m. Now what JEE actually asks. 5 pointers. 1. The sham condition. The acceleration is proportional to minus the displacement, equals minus omega squared x. The restoring force pulls to the mean. 2. T equals 2 pi root m over k for a spring and 2 pi root l over g for a simple pendulum, both independent of the mass and the amplitude. 3. Springs in parallel. The effective k is k1 plus k2. Stiffer in series. 1 over the effective k is 1 over k1 plus 1 over k2. Softer. 4. The energy. The total is half k squared, also half m omega squared, a squared, and constant kinetic maximum at the mean, potential maximum at the extremes. And 5. Phase and damping. Velocity leads displacement by 90 degrees. Acceleration is opposite to displacement, and resonance occurs when the driving frequency equals the natural frequency. Now an assertion and reason drill. For each pair, are both true, and does the reason explain the assertion? First pair. Assertion. In sham, the acceleration is maximum at the extreme positions. Reason. The acceleration is proportional to the displacement and directed opposite to it. Both are true, and the reason directly explains the assertion. The answer is A. Second pair. Assertion. The total energy of a body in sham is maximum at the mean position. Reason. The kinetic energy is maximum at the mean position. The reason is true, but the assertion is false. The total energy is constant everywhere, not a maximum at the mean. So the answer is D. Third pair. Assertion. The velocity of a particle in sham is maximum at the mean position. Reason. The acceleration of the particle is 0 at the mean position. Both are true, but the acceleration being 0 does not explain why the velocity is maximum. They are two separate consequences of being at the mean. So the answer is B. Now match each quantity to its formula. The spring mass period goes to 2 pi root m over k. The simple pendulum period goes to 2 pi root l over g. The total energy in sham goes to half Ka squared. And two springs in parallel go to k1 plus k2. 4 pairs, and each is worth committing to memory. Now, how many of these 3 statements are correct? 1. In sham, the acceleration is always directed towards the mean position. That is correct. It is a restoring acceleration. 2. The kinetic energy in sham is maximum at the extreme positions. That is wrong. The kinetic energy is maximum at the mean, where the speed is greatest. 3. The period of a simple pendulum is independent of its amplitude for small angles. That is correct. So the answer, 2 are correct. Statements 1 and 3. The trap is statement 2. The kinetic energy is maximum at the mean, not at the extremes. Now the 2 mistakes that quietly cost marks. The myth, springs in parallel combine like resistors in parallel with their reciprocals adding. The truth, parallel springs add directly. The effective K is K1 plus K2, which is stiffer. It is springs in series, whose reciprocals add. Springs are the opposite of resistors here. The second myth, the period of a simple pendulum, depends on the mass of the bob. The truth, T equals 2 pi root L over G. There is no mass term at all. The period depends only on the length and on G. Now, test yourself. Answer in your head before the reveal. That is how G speed is built. Here we go. Question 1. The period of a 1 kilogram mass on a 100 Newton per meter spring. 2 pi over 10, about 0.63 seconds. Question 2. Where is the kinetic energy maximum in SHAM? At the mean position. Question 3. Two springs, each of stiffness K, joined in parallel, the effective K, 2K. Question 4. The total energy of SHAM, amplitude A, spring constant K, half Ka squared. And question 5. A pendulum's length is made 4 times longer. The period becomes 2 times because the period goes as the square root of the length. Let us gather it all in one breath. Sheen. Acceleration equals minus omega squared x. The solution is x equals a sine of omega d plus phi. The period is 2 pi over omega. A spring has period 2 pi root m over k. A pendulum 2 pi root l over g, both independent of mass and amplitude. Springs, in parallel the k values add, stiffer and shorter. In series the reciprocals add, softer and longer. Energy. The total is half Ka squared, constant kinetic maximum at the mean, potential maximum at the extremes. And phase. Velocity leads displacement by 90 degrees. Acceleration opposite to displacement. Damping decays the motion. Resonance at the driving frequency equal to the natural. Next class. Waves and sound, traveling waves, the wave equation, and superposition. Simple harmonic motion is one rule. A restoring pull in proportion to the displacement, and from that one rule flow the sine in time, the constant energy of half Ka squared, and one clean period. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack JEE. I will see you in the next class.